Welcome to the screencast that is meant to teach you how to combine uncertainties using a Monte-Carlo simulation. The specific example will be combining uncertainties when you're adding two values that both have uncertainties. So in our example here, we're going to combine 7.431 with an uncertainty of 0.015 meters with 6.379 with an uncertainty of 0.015 meters. And so what we want to do is we want to simulate a whole bunch of measurements based on this 7.431 plus 0.015. That's the first thing we're going to do. So what we will do is we will put our value of 7.431 in there as our value. Our uncertainty is 0.015. And I had this already ready to go. This is what our first simulated data point is going to look like. So remember, we have this notation that is rand, which is a random number between 0 and 1. The norm inv is going to basically convert what's in here into a Gaussian that has a mean of this value, which is 7.431, and a standard deviation of this B5 value, which is 0.015. So what I'm going to do is I'm going to sample this Gaussian distribution, and we're going to do it 500 times. So I've done it once here, and basically we want to fill down 500 cells. One way that you can do this is actually you copy the cell, edit copy, and then I'm going to paste that cell here, and then I'm going to go down, 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 all the way from where I was at until I get to 510. So that will be a total of 500 cells since I started at cell 11. And then I'm going to paste, and there you go. So I've copied and then I pasted it, and as you'll notice, right, the B4 and B5, I've got the little dollar sign holding the 4 and the 5, so it always looks to the right rows for both of those. Just a real quick check to see what those data look like. There's some stuff in the spreadsheet here designed to find how many counts there are in each bin. If you're curious, you can look at that. But the big piece here is that I want to look at my histogram of the simulated X, and I see it looks like I have a mean of, if I look at this histogram, of approximately 7.43, and my standard deviation looks like it's maybe a bin or a little bit more than a bin. So it's 0.01 or maybe 0.015 based on just kind of what the histogram looks like. And I go over here and I remember, okay, right, yeah, so 7.4 and our mean was, 7.43 and our mean was 7.43-ish, just like I was saying, and the standard deviation was 0.015. So this kind of represents this Gaussian represents our measurement that we made. So that, and then we simulated a whole bunch of versions of that measurement, and we got back out something that kind of looks like this nice Gaussian with a width, which is actually equal to our uncertainty. And then we did this 500 times. Now I want to quickly calculate the actual exact average of this. So equals to average, and then, average, and then I'm going to pick all of these. And so I'm clicking on the top cell, and then I'm going to go all the way down to the bottom, and then I'm going to hold shift and then click on the bottom cell, and that will select all of them, close my brackets, and when I go back up here, I see that I have this average of 7.4305, which we ran to 7.431, so it looks like that's basically the same. So our calculated average is the same as the input average, basically. Now, the standard deviation, we want to do the same sort of thing, is equal to STDEV, and then we're going to use the exact same cells. So that was B11 to B510, and we'll close that, and I get a standard deviation of 0.0147, where the input standard deviation for the Gaussian was the input uncertainty, which was 0.015. So those all look pretty consistent. Awesome. I'm going to repeat the same thing for the Y value, and the Y value that we measured was 6.379 with, again, an uncertainty of 0.015. And then I'm going to repeat the same process we had before. I'm going to simulate my first data point. So here, if I look carefully at my first data point, I see that I've got my random number. I've got my mean of C4, which is 6.379, and I've got my standard deviation, which is 0.015, and that's my uncertainty when I'm representing my measured value as a Gaussian. Again, I want to copy and paste all the way down like I did last time, and then I also want to calculate the mean. So I'm going to copy this cell over to here, and now it's looking at everything in C to calculate the average. I'm going to calculate standard deviation, and it's going to look basically down everywhere down here. Again, you'll notice that every time I do something new in the spreadsheet, it recalculates all the random values. This should not be a big deal. It might cause your values to shift around a little bit, but since we've done 500 points, 500 measurements, that this on average should do a very good job. Right, so you can see that the standard deviation is 0.015 to the first two significant figures for each of our distributions. Great. Now, so what we want to do is we want to basically act like, now that I have my x distribution, I have my y distribution, and I'm going to make a random measurement of x, I'm going to make a random measurement of y, and I'm going to add those two values together to get z. So I'm going to say z is equal to x plus y. And so how do I do that? Well, I'm going to go down to this cell here, and I'm going to say equals, and it's going to equal B11, so I'm going to click on this cell, plus C11. So this is going to, the value of this cell is going to equal the x in row 11 and the y value in row 11, and that's going to give me that. And then I just basically want to, again, fill all the way down. Quick trick, you can, oh, it doesn't work here, never mind, not a quick trick. I'm going to go all the way down to here, and instead of copying and pasting, I'm going to fill down, does the same thing as the copying and pasting would have. So now I have a whole bunch of values here that are for my z is equal to x plus y. So now if I look at my distribution of z is equal to x plus y, basically what I've done is I've taken my measurement of x, or my probability distribution for x, and I've sampled it, and then I've taken my probability distribution for y and I've sampled it, and then I have a whole bunch of values for z, and if I look at all those values of z together, that's going to give me a probability distribution for z. So now if I look at the mean and the standard deviation of z, that's actually going to give me my value for z and my uncertainty for z. So I'm going to copy my my code for my mean over to here, and so we'll look at now at E. I will copy my code for my standard deviation over to here, and that will give my standard deviation of E. And then if you look, you see we get this value of 13.809 with an uncertainty of 0.020, which if you did the algebraic one, is very close to what you get. Let's go, as the last thing we do, let's quickly go and look at the histograms, because I've actually gone and histogrammed these. And so if I made all the bin sizes exactly the same, so the scale in terms of where they are along the x is not the same for each of these graphs, but they all have the same size between bins, so I can compare the widths of each of them to understand what the standard deviations look like compared to each other. So my x was a value of 7.43 with an uncertainty of 0.015, and that is, that looks good. My y was, what was it, 6.38 basically, with an uncertainty of 0.015. Okay, that looks pretty good. It looks a little closer to 6.37, but that's fine. And then my resulting one is 13.81, and with an uncertainty of approximately 0.02. So you can see that the uncertainty has increased when I try to combine these two values. I get a larger value. But it's not actually twice as big. Twice as big would have been 0.03. So this is, it's actually the square root of 2 times as big, 1.4 times as big, which is what you find when you actually did the method using formula. So hopefully that helps you understand how you can do combining uncertainties using a Monte Carlo. The neat thing about this is you can do it for really difficult functions like sines and cosines and things like that, or combining just a whole bunch of different values together. This is, once you're good at this method, it's a very quick way of doing combining uncertainties instead of using what we're going to teach you a little bit later, which is the calculus method. So we're giving some equations based on the calculus method right now, but later on you'll be able to derive those equations on your own. But you might find that using the Monte Carlo is a lot quicker. And if you histogram it, it's kind of nice to see how those uncertainties are going. So the uncertainty in x plus the uncertainty in y is going to give us an uncertainty of z if we add them in quadrature.